All right, finally, last lecture on my research related. So this is the data, the measurement of structure function F2. I showed you this plot previously. So it's there's two observations here. One is it certainly increases rapidly as you go from. So this is a function of x and q squared. So in this case, it's focused on the dependence on x. So it's plotted with, not plotted, the data showed that as you go to smaller and smaller x, you have a rapid increase of your structure function f2. And another is you can see that when you have larger value of q squared, this increase becomes even stronger. That's what these data tell us. And I believe these lines are from the fading based on the DigLab equations showed you in the previous lecture. So this data certainly there's an implication or message from this data is that the proton contains a rapid increase in density of small x partons. Remember that F2 is, at least in the collinear factorization, is a convolution of hard factor and PDF. PDF is the proton distribution function. So you can imagine that a small x region, your proton distribution function is very large. And it turns out this is not the valence quark, but actually the gluon still. So you can also have a more visual representation from when people extracted the PDF. Is you notice that it's not just f, it's x times f here. Actually, that's what is quoted here. The red lines are for the gluon. This scale is already scaled 10 times down here. You can imagine if I do not scale 10 times, it will basically one order of magnitude larger in the distribution, the small x region. So how do we actually understand that? Or qualitatively, semi-quantitatively from the DigLab equation. So these are the two sets of equations. In this equation, I set the factorization scale with q squared. I want to focus on the small x region. Basically, I want to I look at the x dependency on the right-hand side of my equations is in these splitting kernels. So I want to look at what the splitting kernel will look like in this small x region. So in the small x region, the ratio will be very small, much less than 1, so that if you stare at the expressions of these splitting kernels, you can immediately realize that the dominant contribution is from this gluon to gluon and quark to gluon. So these are either your gluon will fuel your gluon production or your quark will fuel your gluon production. The production of quark actually is order of 1. They are much smaller than the production, the generation of quarks in this splitting. So essentially, it's the second part that is important, that gluon will increase. So in this case, you can essentially ignore this first term because your quark is not catching up with the increase of your gluon. In that case, the coupled equation essentially is dominated by the pure gluon part in the small x region. So you only, instead of two coupled equation, you have one equation that tells you the scale dependency of the gluon distribution. You can try to solve this equation. First, you can redefine by multiplying your gluon distribution by this x, as I showed you previously. This is where the plot is quoted as x multiplied by the PDF. And then this equation can basically move that factor to the left-hand side in the numerator there. and you add a z there, and you have 1 over z here. Then you try to solve this equation so-called iteratively. You can put a leading order on the right-hand side. You feed here, you solve the expression, and then you feed there order by order. And it turns out all these orders can be resummed in this exponential form, which is square root, you have a log q squared and log -1 over x. This is the so-called double logarithmic approximation for the ground distribution, because you have 2 logs here. One is from the transverse momentum integration of q squared over q0 squared. The other is the 1 over x. So this particular form at least gives you a qualitative understanding of this increase there, because when you have smaller value of x, your log is very large, it's exponential, it's a level of growth. And when your q squared is large, this growing rate is also larger, it's faster. So just from this developing this double logarithmic approximation, you have a fairly good understanding of this, qualitatively, this behavior. The full fitting here, of course, is used, the 4 Diglab equations and all the splitting functions calculated to 3 lobes and even more. There's a more theoretical message from that data I showed you. So it tells us that this ground distribution grows rapidly as your value of x becomes very small. But if you look at the Diglab equation and also the FKL equation, which we'll talk about at the end of this lecture, that these equations are linear equation. They predicted that your gluon can be generated by splitting your partons. You can have, for example, here, you have a proton, and they can radiate gluon. That gluon can radiate to another gluon, or it just fluctuates into quark-antiquark pair, and additional quark can radiate gluon. So as long as you have a very large energy window you opened, you can keep this splitting and radiation going on. But this process cannot continue indefinitely. Otherwise you will have infinite this cannot keep increase, because eventually, if you think of this as some probability distribution, you eventually will violate your total probability to be 1. That's usually what unitarity means. So this means that at a certain point, it should stop increasing, which means in that case, it's saturated. The physics behind this particular saturation of this increasing with small x is eventually, when the gluon density is large, the inverse process of gluon recombination will become important. Instead of keep splitting and splitting, eventually you will have the gluon recombination that will compensate the splitting, which increase the number of gluons, and you have recombination, which will decrease the number of gluons. That's when the balance is achieved. That's what theoretically people expect this will be the gluon saturation there. It's like a general picture. So we want to, now we'll discuss more mathematically, rigorously. We want to talk about gluons, because gluons is important in the small x regime. So we should first revisit how gluons enter in this form, in this Bjelken limit. So because we are in the small x regime is the Regge limit, but we didn't talk much about this gluon contribution in the Bjelken limit. So now we want to briefly outline how it also works in this Belkin limit. So if you look, again, the starting point is theoretically, starting point is always, yeah.
So like at a certain point, it would stop splitting to a like so-called a certain equilibrium. So can you view certain like a phase transition?
Phase transition.
Like in thermodynamics. Phase.
But it's not necessarily a phase transition. In thermodynamics, you have equilibrium. Okay? I'm not so sure in what sense of the phase transition.
So just like a quantum many body systems, under certain condition, you can have a phase change or phase transition.
Yeah, that's usually, for example, in thermophysics, you have some thermodynamic quantities like heat capacity, for example, which will have some discontinuity across some parameter space of pressure and temperature. That usually gives you the phase separation lines. This is more, I'm not sure. I never saw people talk about this in the language of phase transition. I'm also not quite sure what are the different phases we are talking about. So yeah, I really don't know how to make this analogy in that sense. So the word may not, I mean, the name, the terminologies may be similar, but the physics are different. Also, it's not so clear whether you have is it a thermal system inside the proton?
The definition of a thermal system is
right up to now, what we talk, okay, you can think of it's a money body system, but the way we are talking about this proton distribution function is like I have sufficient high energy that I can somehow kick out all my protons from my proton. So it's more like if you have a system of molecules, you have something, you kick a molecule and you want to find out how the molecule is distributed inside your system. It's not in that step like I want to consider the thermodynamic system of proton. Oh, maybe I think maybe next week there's some speaker talking about I don't know, mechanical properties of the proton or pressures. Maybe you can find a better analogy then, because somehow they are using some similar terms like, for example, pressure inside the proton. Which usually is for some systems. Okay. So we always start from, theoretically, for theorists, we start from this hadronic tensor, W mu nu. How do we generate gluons? So if you look at the electromagnetic current, so this is basically direction. So you only have the quark in that current. So if you directly plug in this expression, you don't have gluons there. But if you try to understand how the diagrams is drawn here, you immediately realize that these gluons can be understood as the propagation of your quark and antiquark in the fields of gluons. So instead of when you do the weak contraction, instead of a vacuum quark propagator, you have the propagator in the background of ground field. So you basically contract the two. You have four fields. You contract the two pairs. That's how you generate the two propagators there. The propagator inside in the background of ground fields can be. So since I'm only generating gluons, I'm not in. I think Roberto also said in some case you can have additional attachment or quark or gluons. Since I have these diagrams in my mind, so I will only consider gluon insertions. We have propagator, S0 is free propagator, and they have an insertion of gluon field, and then after that you continue propagate at the free particle. You can insert more. So in space-time dimension, so these are not in momentum space, but in coordinate space. If we want to have a ground distribution, we need to keep the ground field to second order. So if you put these expressions, the propagators, to this expression, then eventually you can simplify, and your hadronic tensor is still convolution. It's a momentum k. You have the hard scattering part, and you have the non-perturbative part, because you have two gluon fields, and they are the operators that averaged between your proton state. So I didn't give the explicit expression. It's not relevant to discussion now, but you can imagine there's some expressions of this hard scattering part will be there. At this step, it's just like in the case of quark contribution, your full four components of your momentum are convoluted between these two factors, and then you can do the similar manipulation doing the so-called collinear approximation. You assume your gluon is the dominant component is collinear to your proton, so that the plus component is an important one. And then that the plus component will enter the interaction with your hard factor here, and the rest of the components of the momentum is part of your proton structure function. In that way, you can get the gluon distribution. So eventually you'll have like the collinear factorization involving the ground PDF in this form for the hadronic tensor. So this is not easy because you don't have, this is the field strength tensor, F mu nu in the component of plus I. You only, in this diagram calculation, you only have a field, the gluon vector potential. You still need any procedures to eventually get this expression, but the general idea is you have these diagrams, and these diagrams will tell you the convolution of this, the convolution of these hard factors with a ground PDF, and that will be the contribution of the gluons to the hadronic tensor. That's how you do this in the collinear approximation, like the case for the quarks. Okay. Then how do we do this in the Regge limit? So in the Regge limit, the scale, that the large scale is not the Q square. Remember, we have the leading power expansion. We have lambda QCD square over Q square. That's what we truncated. But in this case, Q square is not large. What is large is the S. S is the central mass clearing energy of your virtual photon with your proton. You have very large clearing energy, but the virtuality of the photon is not necessarily very large. So you can imagine that I have a small parameter, but not 1 over Q square, but rather Q square over S, or 1 over S. If I have a small parameter, I basically can perform some expansion in terms of 1 over S, like what we did in the leading power 1 over Q square, that will give us a way of systematically organizing contributions. Do you have a small parameter? You probably can do a lot of physics with it. So in this case, it's also easier to do the calculation not directly with this cut diagram. So you have final state all possible x there. Instead, we can consider the forward scattering amplitude. So instead of so because they are related with the imaginary part of my forward scattering amplitude. Through the similar ideas to the optical theorem, probably you already, if you took a QFT course, you probably know this optical theorem. Again, so we basically, so the forward scattering amplitude compared to the W mu nu has this additional theta function to tell you that while this part happens before that part, so you need to make sure that there's a time order in these two currents. And again, you still want to contract because these are electromagnetic currents. They only contain quark fields. You still want to contract the fields into propagators. In this case, the so-called Regge limit, something nice happening. Remember, in that case, you only have 2 gluons involved, right? So you can certainly calculate more, but the expression will be more complicated. The nice thing in this Regge limit is actually you can resum all these possible gluon exchange in one simple term in the so-called Wilson line. Because you organize this differently, in this Regge limit, only one component of your gluon field is the dominant one. That one can be resummed. So basically, that's the general picture. So I should go back. So again, this is similar to what I showed you, how the free propagator and then how the interaction inserting this gluon exchange. But in this case, this gluon insertion can be resummed to all orders in this form, also called Wilson line here. So you 1 gluon, 2 gluon, 3, 4, all these possibilities are summed into this exponential form. That's the nice thing that happens in the Regge limit. So this expression is not difficult to derive. So if you consider, you just do this one by one. First, you start with 1 gluon, and then you consider 2 gluon, 3, and then you find the pattern that you basically form the like Taylor series expansion with some exponential function. You resum into exponential form. The way it turns into this simplified form is we look at the so-called diagonal approximation here. So this is the full propagator. But if the quark has a very large minus component, that is the dominant one. So your transverse and plus component it is full. So you have P slashed, which is P mu gamma mu. So then you should have P plus gamma minus gamma plus gamma I Pi. So this is a dominant component because your P minus is much larger than P plus and your I. So you decided, oh, in this limit, I'll just keep this term. So that's my numerator there, numerator. if I look at my my denominator, I have p squared, so which is 2p plus p minus p perp square. So again, this is the largest component. So I'm doing a very crude approximation here. Sorry, I just keep the leading contribution. Then my propagator is simplified in this form because this term and that term, my p minus is canceled. That is the form. So for the p minus part, your Fourier transformation will give you a step function. The other part are just the Dirac delta function. And the spinor structure gamma plus is left there. So the reason why it can be resummed in a simple form is because your propagators will be dramatically simplified. You are not using the full propagator, but the so-called iconized repropagator there. You can put all these intermediate propagators in this iconized form, and then it will give you this structure here. I use a different notation. Yes. Different notation. So this is important because all the contributions of gluon is not in terms of single gluon field, but it always appears in terms of this Wilson line. Or it's always in this form, not as a single gluon field, because you can always do the resummation in this term. So you have an expression for the gluon propagator. You can put in this expression. You can imagine I have two propagator. Then I should have two Wilson lines in my final expression. So that basically gives me the form, this factorized form. Let's see. So we have this part. This n, the next slide, is the two Wilson lines from the two propagators. And I use the shorthand notation that this angle bracket is basically representing the matrix element of these Wilson lines between the proton state. Go back. This is the matrix element, which is the non-perturbative part. And then you have the hot scattering part is expressed in this particular form, the so-called photon wave function. So you can further evaluate if you like, but this is the general definition of this photon splitting wave function. I think maybe this picture is better to explain what happened. So you have the photon wave function essentially is you have a virtual photon coming in, is split into quark, anti-quark. That photon wave function tells you how this splitting happening. So once the splitting happens, your quark, anti-quark will scatter with your proton iconally using that iconal propagator. And then after that, they will combine to form again a virtual photon in the forward region. That's basically how this expression tells you it's like I have two wave function, and then I have the interaction with the proton. The convolution certainly is not previously the convolution is through QCD, which is the longitudinal momentum fraction. But now this convolution is R-perp, which is the transverse coordinates. So the R-perp is the distance or between your quark and your anti-quark. The reason why is, so the formula is not written in momentum space, but it's a mixed representation. You have still have the QCD, but it's only related to the hard scattering part. The convolution is in coordinate space because the iconal case, if you have a quark propagating, like for example this diagram, it does not change its transverse predation. So you have, if you have X perp before you interact with your proton, you exit still as a transverse predation diode. That's what happened in the Eikenau case. You pick like a color rotation because this Wilson line is in this TA is a generator of a SU3, so it's a matrix in the color space. So you pick a color phase rotation each time you interact with your proton. That's eventually give us this expression. And of course, this is the only approximation. In the Regge limit, we only keep the term that is leading in the 1/s. If you compare with the collinear case, it's 1/q² correction. So any questions about this factorized form, or any questions about the way it is presented or interpreted? So it's a different kinematics. So in the
I wonder the later diagram, is this the econo gator? Is that only an approximation?
which one? This one?
Yeah.
This is the, so first of all, we are always making approximations.
Oh.
In the collinear case, we have the approximation. The collinear factorization is correct only when you ignore 1/q² fraction.
Yeah. Just
This is also this is correct if you ignore 1/s correction.
okay. So why didn't the Coulomb split?
Coulomb split, that any Coulomb splitting will not contributing in the 1/s. It will be higher order in the 1/s expansion. You can certainly consider this. Maybe you can put a Coulomb, for Coulomb interact with your proton, maybe it will be interact with other gluons and all these stuffs.
So the gluon splitting will be suppression, right? In that limit.
In this case, there's no in this case, there's no gluon splitting. These gluons are all exchanged gluon. But if you consider so beyond, okay, we all have a gluon splitting next leading order later on. But it's not so I think at this step, this form of the propagator in the background field is true that I only keep the leading 1/s contribution there.
And my next question for the factorization formula, which one is non-perturbative?
Oh, this no, this one is non-perturbative, this n, because n is a matrix element between your proton wave function. So it's not just that two gluon field, now they enter in this Wilson line form. So previously in the collinear factorization, I showed you that, oh, this is a non-perturbative part. You have proton wave function because you are exchanging two gluons, so you have two gluon field. This is what happened. That's the non-perturbative part when you do collinear factorization. But in the Regge limit, you can actually resum this all the gluon exchange, not just two, into this form. And when that is averaged between the proton state here, that's the non-perturbative part. So it's not two gluon anymore. It encodes many gluon exchange. That's what happened if you do an expansion in powers of 1/s. So what is this? The gluon fields enter this non-perturbative object through the Wilson line. So what is this Wilson line correlator? We have two Wilson lines at different transverse position. It turns out this is related to the gluon distribution function, but you need to take the limit of x goes to 0. And it's also for the transverse momentum distribution. So if you start from the general operator definition, this is the more it's the same form as the one I showed you, but it's written in the fundamental representation in the column matrix space. So you have two field strength tensor F plus I, F plus J, but they are connected with gauge links so that the whole expression is gauge invariant. So you can imagine that you have two fields here. How do you connect them so that the whole expression is gauge invariant? There are many choices. So the so-called dipole case is you have two gauge links. One is going future pointing, the other is past pointing gauge links. But if you put two different gauge links here, you will have different types of gluon distribution function. This is not like PDF because it's transverse momentum dependent. In PDF, remember you have Q square, which is essentially integrate your transverse momentum all the way to Q square. So if you start from this expression, you notice that there's a dependence on x in the exponential. You try to expand because x is small, you expand at the power series of x. It's not just expand this phase because you have a derivative on QC minus in this expression. You need to integrate by parts and then do the expansion. So at the leading order, when you set x equal to 0, that's what you end up with. This Wilson line automatically shows up in the expression. So this Wilson line correlator, and in this derivation, I use the V, essentially it's the same as U here, as long as they are both in the fundamental representation. So this Wilson line is the transverse momentum dependent ground distribution function. It's not something purely mathematical construction. It has the meaning of the transverse momentum ground distribution function, but it's only in the regime of x very small. Okay, so back to the factorization form. So you still have this part is the hard scattering part. You have the non-perturbative part. The non-perturbative part represents the ground distribution, transverse momentum ground distribution function inside the proton, but it's only valid in the small x. Or in other words, this expression is only valid in the leading power of 1 over x expansion. So that's the leading order expression in this particular form. So you have the photon splitting and scattering, and then back combining. Like what we did in the collinear case, we all need to consider next to leading order fractions. At the next to leading order, you can imagine that instead of just a photon, a virtual photon split into a quark, anti-quark, you can have a gluon, maybe splitting. You can have a gluon emission like this. Or you can have just like what happened in the previous lecture, you have a real gluon emission, or you can have a virtual gluon correcting your pre-propagation. So one gluon emission order alpha s when you square it. As next to linear order, you will have such diagrams. It's exactly the same types of diagram. It's just topologically it's drawn in a slightly different form. So at next to linear order, you will have Coulomb splitting, not Coulomb splitting, you will have more partonic state that will eventually, maybe this will interact with your proton state. If you try to calculate these diagrams, these are one loop diagrams. So you have instead of a large transverse logs, you have a large longitudinal log, which is have the log 1 over x. When x is very small, you have a very large number, which is order 1. So these large logarithmic terms must be resummed to all orders, because if it's order 1, any fixed order calculation is insufficient. All these terms are comparable. Right, so this is trying to making an analogy with the Dirichlet evolution equation. In the case of a Dirichlet evolution equation, we resum this. It's an evolution with Q square. Essentially, we resum this large logarithm, transverse log. The small x case, we want to resum this log 1 over x. And these large logs in the Dirichlet case is associated with the PDF. In this small x case, not PDF, but the Wilson line correlators, that's the non-productive object. So in that case, in the Dirichlet, it's evolution with respect to Q square. In this small x case, it's evolution with respect to this little x, or equivalently with respect to the rapidity y. So there are the most general form is called Jim-Walk equation, named after these authors. It was developed in the early around 2000. This equation is the rapidity evolution of the probability distribution of the Coulomb fields inside the proton. This equation this equation will generate coupled hierarchy of Wilson line correlators. It's not a closed form equation, but if you take the so-called large NC limit, or the mean field limit, you put the number of colors of in QCD to be very large, the equation actually becomes a closed form, which you can actually solve. This is so-called Balinsky-Kovachukov equation. So if you try the diagrams that contributing to the BK equation are just like this. As I said, you can imagine I have a photon here. I didn't draw the photon on the two ends. You can imagine you have a photon here split, but one quark will emit a gluon, and the whole thing will scatter on your proton. And each time is iconal propagation, and it will pick up the iconal phase there. So you have the real emission diagrams. You also have some virtual emission. Just imagine you have the virtual photon on the two ends. Diagram like this. So these are the diagrams that will contribute to the derivation of the BK equation. So eventually, this is the form of the evolution equation. So I showed you that n, that is what interests the factorized form, representing the non-perturbative physics in this hadronic tensor. So we find the evolution of the dipole amplitude as a function of rapidity y. So if you look at the right-hand side, there are linear terms, linear in the dipole amplitude n. And then you also have a nonlinear term, which is a quadratic in the dipole amplitude. So you also have this kernel here, which essentially you see you integrate over the transverse coordinate z. That integration is essentially because you radiate the gluon, your gluon can be in any, your transverse position of gluon can be in any transverse position here. So you need to integrate over all the positions of that gluon. That z is the transverse position of the radiated gluon. So the linear term represents the gluon splitting, and it will contribute to the increase of your dipole amplitude with respect to your rapidity, y. And then you have a nonlinear term of the minus sign here, which essentially describes the gluon recombination effect. You can imagine that when n is very large, this term is larger than the other terms, they will dominate. But when n is very small, the linear term is dominating. So this BK equation essentially will balance the increase of the gluon distribution with the decreasing of this, or the recombination of the gluons inside of the proton. Does this make sense?
Is this all before taking the large NC limit, or do you just?
The NC.
Okay, so you just throw out anything like quadratic and NC, or?
The terms that, so the nonlinear term there, if you do not take large NC, it will be 4 Wilson line, something like that.
Right.
Sorry. We have X. It's probably in this form. So if you do not take large NC limit, it will be 4 Wilson line. It's not the one we are interested. We only want 2 Wilson line because 2 Wilson line represents the ground distribution. If you have 4 Wilson line, basically it's like a 2 gluon correlation, not a single particle distribution anymore. We want to take large NC limits, essentially it decouples in that way. Because the terms you ignored is NC suppressed, so all this.
Yeah. Yeah, okay. I think I was just confused as to when you apply the.
This is already the final form,
That's
already applied the large NC.
That makes more sense, yeah, yeah.
So as you can see that there's only one object, which is n in this equation. That's why it's a closed form. Otherwise, you have other objects, you will need to derive the evolution of other objects, and then you couple to new objects that will generate a hierarchy system of equations. Is not solvable. So this is the BK equation containing the nonlinear term. You can take the so-called dilute regime. You assume this object is very small so that you ignore the nonlinear term. You only keep the linear term here. So this is a form that only containing the linear term. If you try to make a Fourier transformation, so there's a caveat here. It's not the strictly speaking, it's not the usual Fourier transform you are familiar with. There's an additional factor, but if you make the transformation into momentum space, this equation will generate the so-called BFKL equation. Some of you might be familiar with, was developed like 50 years ago. So this is this BK equation is a generalization of the linear gluon evolution, or linear amplitude evolution, by including this nonlinear gluon saturation effects. So this is actually a very good cross check once you have some results. You are consistent with previous results in certain limits. The most important message from this evolution equation is there's a scale, dynamically generated saturation scale from that equation. You have the physics there. So this balance, because this amplitude has in certain sense has a minimal probability, so you want to set this to be 1/2 when the transfer size is at certain scale. If you do that, you can get an expression by solving the BK equation analytically that this scale is in this form, is exponentially related to the rapidity and the power law dependence on the value of x. This can be determined analytically. It's related to the di gamma function. It's the first order derivative of gamma function, and it can be numerically calculated. That basically gives you the energy dependency of this scale here. So this scale separates the linear growth of your gluon inside the proton with your nonlinear recombination effect. However, this last slide is more. This cartoon basically shows you how you actually look at the internal parton distribution inside the proton. So it really depends on what probes you want to see inside the proton. If you use a very large transverse resolution scale, if you have higher values here, you see finer and finer structures there. So that basically what the Diglab evolution equation will lead you to this or finer partons inside the proton. On the other hand, instead of resolving the partons with finer transverse resolution scale, if you fix your transverse resolution scale, instead you look at your longitudinal momentum, look at the splitting of your partons. More and more partons will split, eventually they overlap and they start to recombine to form an equilibrium state. So that's the general saturation region. Right, I think this also highlights the idea of if you want to understand the X and the Q square distribution inside the proton, the physics really depends on what region you want to study. Different regions will require different theoretical tools to systematically organize your first isolate your dominant contributions and then systematically organize all the corrections. Yeah, I think that's all the contents of this last lecture.
Thanks a lot, Ming, for the detailed lectures. And now the time for questions. Ewan? Questions?
Thanks for your lecture. I wonder how is the theory correspond with the experiment?
So,
How well they correspond?
well, first of all, this I think the One of the important goals is to find whether this so-called saturated Coulomb state exists or not. So you can derive this equation following the rules of QCD and within the assumptions you make. For example, we are considering the high collision energy limit. You have this equation, it predicts that this state of gluons with very high density and they are saturated. And certainly the more experimental related question is does this state really exist, or can we actually detect such state, and what observable, what signals from experiment we can isolate that directly telling you, oh, this is due to this from this state. That is one line of the experimental efforts people or theoretical efforts people are doing. But I don't think it's from this inclusive DRS, because up to maybe in the future, because this data, this F2, it can be explained very well. You don't need this big equation or BFKL. You can just use DGLAB, and it explains pretty well. At least that's the current state of the consensus of the field. So this does not tell you that. But you should also notice that this double logarithmic prediction can also get this from solving this BK equation. So this is kind of an overlapping region, because the simultaneous amount some small x and large q square, you have two regimes, they have some overlapping regions. So this is not. I think what people are looking at is more exclusive observables. You have some final state correlations you want to isolate, so that will tell you more information about effects from this saturated Coulomb state. But right now, at least one goal of the future electron-ion collider is try to look for signals of possible Coulomb saturation and the onset of nonlinear Coulomb dynamics. But right now there's no conclusive data from experiments saying that, oh, this is a new saturated Coulomb state. For now, this is a lot of theoretical efforts, but no conclusive. There's no conclusion from experiments.
Okay, thank you. The next question is, what are theoretical people like right now? What is the frontier?
Oh, the frontier. There are a few. Well, first of all, this equation was derived like 20 years ago, and then both analytic solutions and numerical solutions were, you can imagine that, quickly obtained. And then people realized that, oh, I have a coupling constant in this alpha S. What scale? Remember in the first lecture, we have a rounding coupling, right? It depends on some scale. What rounding coupling should I put there? Then there were efforts trying to have the so-called next leading order correction, because at next leading order, you have the rounding of coupling. And next to leading order, then there are some problems there, and people try to improve that. But currently, people use the next leading order, the equation. With the next leading order, people started to think about, oh, I will calculate the inclusive DRS also to next leading order, and also other scattering processes to the next leading order. So it's more like a precision frontier. I want to push this framework to higher order in coupling constant. That's one direction. The other direction is similar.
Sorry, you mean next to linear order is for the hard scale, right?
Next to linear ordering coupling constant, not in the expansion of not in the expansion of 1 over S.
Okay, but I know in in the collinear factorization, they have already calculated to for loop. So why this is like only to the NLO?
You do this step by step. You see, you first need to finish NLO, and then you calculate NNLO, and you probably need enough manpower. Suppose you have 1,000 theorists, they probably only finish the for loop calculation, but you probably only have, I don't know, maybe it's a small area, not as many theorists doing linear physics. So they eventually, there's also, okay, regarding your question, there's also the motivation why you do next to leading order, next to leading order. There's a motivation from experiments. When they compare with data, if your leading order result is already sufficiently good, why do you do the next to leading order? Small correction. I think when people do next to leading order, it's like there's really improvement from if you do that and when confronted with data. That's a good motivation why people do that. Otherwise, why do you stop at the next to leading order? Just because you can. Doesn't mean you should do it. Right? I mean, I think the main reason is probably people, we don't have, there's no data motivating you, you must do this. And then there's also not so many people in this field. And when people do leading order, next to leading order, the next to leading order is some incremental development. You see, there's a rewarding is not, you will be rewarded by doing the next to leading order result. But there's a lot of reasons, some from physics, really data driven. Some people think, oh, it's not worth the efforts. But there are efforts going on, people try to push this to higher precision. That's why frontier of this research. Another is try to push the corrections I ignored here, 1 over S, just like in the collinear factorization. People try to add this 1 over Q squared correction there. So there's also that. And the other is, there's also, this is more theoretical developments. Phenomenologically, they try to apply this idea to other analytic clearing processes, like not just in DLS I discussed, but also in proton-proton clearance, proton-nucleus clearance, even in nucleus-nucleus clearance, to see if any experimental effects or phenomena can be explained from this perspective, right? To expand the application of this framework.
Oh, thank you.
Yep, I want to ask about, so the Coulomb background field, can it be like a semi-classical field? Like you do it?
Yeah, basically that's what, yeah, that's basically the picture we used.
So
especially, I think in the early days, there was this argument that, oh, because your Coulomb number density is very high, so if very naively, I'm not sure if you buy this argument. So in quantum mechanics, you have, okay, I have this A, right? This is this is 1, right? In quantum mechanics, you have E diagram A, like a harmonic oscillator, right? You create one harmonic mode, harmonic oscillator mode. So, but you also know that this is kind of like a number operator, right? Don't don't know this. So when this number is very large, you can ignore this commutator effect. Essentially, it's like a classical system. So that's why they in the early days, they started phenomenologically, not theoretically. That's the physical picture they used in the early days of the development.
So
So okay, maybe one more comment. In the collinear factorization, maybe I should, in this case, you do the collinear factorization. That gluon is collinear to your proton, meaning that the plus component of gluon is the largest component. So this is a collinear gluon. It's gluon. In the small x physics, I think it's more like the so-called Glauber gluon. You have a very small x, meaning that the longitudinal momentum is not dominate, but the important thing is its transverse momentum there. So it's two types of modes of gluons you are actually probing. Back to your question, is indeed the classical field we used, or you can understand it in that way.
yeah, what I mean is like, how can we see the classical approximation here or semi-classical approximation?
Classical approximation.
Like as you said, it's a strong background field, so you can treat it like semi-classically. So what is the similar thing here? It's just the iconal approximation.
Oh, okay. Okay, maybe I should answer this way. So if you have this object, this n is the average of two Wilson lines between the proton state, right? This is non-perturbative object, but this, I mean, you probably, I imagine or know that even though it's not calculable systematically, people can always come up with some models to do the calculation. So there's this semi-classical picture or semi-classical framework. It's known as color glass condensate framework. So you calculate the classical field, and then you try to average this, calculate this object semi-classically. The form of that expression will tell you that it's indeed a dense Coulomb field in that semi-classical approximation. The dense in the sense that it's 1 over, the number density is 1 over j squared. It is a strong coupling constant. Or if you want to understand very naively, you have this the strength tensor. In the first lecture, we have this linear term, and then we have this nonlinear. Sorry, this is a kinetic term. This is the interaction term. So in the saturation regime, we have a dense Coulomb field. Typically, it means these two effects are essentially on the same order. You do perturbation theory, you always treat this J is very small, and this interaction is very small there. But in the saturation regime, these two are on the same order, meaning that your field has to be 1 over J, so that this term is 1 over J. This is also 1 over J. If you have a mu in nu square, that will give you 1 over J squared. This is the dense regime people were talking about or argue. This is the regime they are expecting.
Okay, then I think we should, this is nice time to stop.